So, welcome to today's session. So, I hope the screen is visible. Yeah, sorry for the disruption. So, let's begin. So, the main concept is, main concept was supposed to be about the Stern-Gerlach experiment, but there was not many questions from that topic. So, we'll generally discuss about the angular momentum and some questions on Stern-Gerlach, etc. So let us start with the straightforward question. So given the given a state in the standard angular momentum basis L comma m, so of course you know L is the L square eigenstate and m is the mz eigenvalue, and small l is total angular momentum quantum number. So Lm is the simultaneous eigenstate of L square and Lz. So in that basis we have to find the expectation value of Lx square. So how to do that? So it is pretty straightforward. So we know, so we define the ladder operators L plus and L minus in terms of Lx and Ly, and we know that L plus and L minus have a straightforward action on the basis states in the L comma m basis. So using that we can easily find Lx square expectation value. So we know this relation. So these are ladder operators in terms of Lx and Ly. So of course, so Lx can be expressed like this. Just add these two and divide by 2. So Lx is half of L plus L minus. Now let us square this Lx and we can easily find the answer. So Lx square will then give you this thing. Now expand the square and keeping in mind the orders. So you know that L plus and L minus do not commute. So the commutator of L plus and L minus is what? 2Lz. So they do not commute. So we have to be careful about the ordering when we are expanding the squares. So L plus square plus L minus plus the opposite order L minus L plus L minus square. So this is the expansion of the square. Then now what to do? So we know how these L plus and L minus operators act on the gate L comma m, right? So the action of L plus is given by this. So L plus increases the Lz eigenvalue by 1 unit but keeps L square eigenvalue same. So similarly, this is the action of L minus, which lowers the eigenvalue of Lz by 1 unit and keep the L square eigenvalue same. So these two are the action, and this front two So this is the coefficient that ensures that your old L comma M kets and new L comma M plus 1 ket both are normalized. So this coefficient comes from that demand. So note that there is a little difference. So this is the coefficient for L plus, which is L plus 1 minus M plus 1, and this is the one for L minus. So this is L into L plus 1 minus M into M minus 1. So this is the little difference between these two. Now, using this knowledge, let us proceed to actually calculate the expectation value. So we can straight away see that if you act twice with L plus, so your M eigenvalue will be M plus 2. And if you act twice with L minus, your Lz eigenvalue will be lowered by 2 units. And of course you know, so L comma M, if we take inner product of L comma M bra with L comma M plus minus 2 ket, that will definitely be 0 because of the orthogonalities of this L comma M basis kets. So that means these two expectation values are 0. So now we have only remaining 2. So we have these two. Let's see what contribution they give. So we have seen that expectation value of L plus square and L minus square are both 0. Now L plus L minus acting on L comma M. So of course let us first act with L minus M. So this gives rise to this factor, and this lowers the M eigenvalue by 1 unit. So this is L plus acting on L comma M minus 1. So this L plus is this one, as you understand. So now from here let us act with this L plus also. So now you will get the a new front factor, and M minus 1 will be again back to M because L plus will raise the Lz eigenvalue by 1 unit. Now let us look at the front factor. So for M, so if we look at this, so for M it was L into L plus 1 minus M into M plus 1. So we have to put M minus 1 in place of M. So if you put M minus 1 in place of N, of course you get L plus L into L plus 1 minus M minus 1 into M. So this is what we have got, and you can see these two are exactly equal, these two highlighted factors, and so okay, so these are equal. So the square root will be squared, and you will get this thing to the power 1. So similarly, L minus L plus acting on L comma M will give you this. So proceed in exactly similar fashion and you get this result. Now collecting all the contributions and adding, we get this. And upon simplification, this gives rise to this. So this is the answer. So similarly, you can calculate the expectation value of Ly square also, and you will see that you will be getting the same result. So the result is, in the Lz eigenbasis, Lx square and Ly square expectation values are same. And you know that the eigenvalue of Lx and Ly are 0. But the eigenvalue of Lx square, sorry, the expectation value, sorry. So you know that the expectation value of Lx and Ly in a Lz basis state is 0. But here we see that the expectation value of Lx square and Ly square in the Lz basis state is non-zero. So that means so there is a delta Lx, so there is non-zero delta Lx and non-zero delta Ly. So this concludes our first question. So don't think there is any question. It was very easy. So let us move on to the next one. Now the question is this. Consider a Hamiltonian for a spin 3/2 particle. So the Hamiltonian is given. So given this Hamiltonian, we have to find the energy levels. So Sx, Sy and Sz are the spin operators of the spin 3/2 particle. So here C and D are two real numbers. So given this Hamiltonian, let us find the energy levels. So as you understand, so since this Hamiltonian is given in terms of spin components, so we expect some spin eigenstates will be the Hamiltonian eigenstates also. So let us first try to find out the simultaneous eigenstates of Hamiltonian and some spin components. So look at this thing. So this is Sz, and we know that Sz does not commute with Sx square or Sy square, but Sz only commutes with the total A square. See, so we can take so if we take this Sz as one observable, then we can see that the Hamiltonian also commutes with A square. Okay, so let us first look at this form. So the Hamiltonian, of course, can be written in this form. So we recognize this Sx square plus Sy square plus Sz square to be the A square total, right? So it's just adding the square of the components. So this is the total A square, and of course we have separated out this minus 2Sz square. So that means our Hamiltonian can be written like this. Now it is very much recognizable that the simultaneous eigenstates can be taken to be that of A square and Sz. As you see, so Hamiltonian commutes with Sz because Sz commutes with A square, and of course the Hamiltonian also commutes with A square because A square commutes with Sz. So we have observed that this happens. So we can take the Hamiltonian eigengates as the simultaneous eigengates of A square and Sz. And of course, that eigengate is denoted by S comma M. So S is the equivalent of L in the previous problem, and M is Sz eigenvalue. So A square, so this is the eigenvector relation for A square. So A square acting on S equal to 3 by 2 comma M state gives you this. So this is S into S plus 1 H cut square. So A square acting on S comma M gives you S into S plus 1 H cut square and multiplied by that state. So this is the eigenvalue equation for S square, and for 3 by 2 S into S plus 1 is 15 by 4. So this is the S square eigenvalue for S equal to 3 by 2 states will be 15 by 4 H cut square. Okay, that much is fine. And now Sz eigenvalue. So this is simply mh cut, and since S is 3 by 2, M can take values plus minus 3 by 2 and plus minus half, because all the higher other M's are not allowed. So only these 4 values for M are allowed. So collecting everything together, so now we have found the S square eigenvalue eigenvector relation and Sz eigenvector eigenvalue relation, and we know the Hamiltonian eigengate will be the simultaneous eigengates of S comma M. So putting everything together and looking at the Hamiltonian that is expressed in this form, so we finally write the eigenvalue eigenvector relation for the Hamiltonian. So this. So C by H cut square is square. So this A square gives rise to 15 by 4. This 2Sz square gives rise to this 2M square here. And this minus dsz gives you this minus dm. So this is the eigenvalue. Now of course you have only 4 state, so corresponding to S equal to 3 by 2, M can take only 4 values, so you have only 4 states. So your quantum system here is 4-dimensional. So put the values for allowed values for M, and you will get the energy levels corresponding to each of those 4 levels. Okay, so in assignment, I think you need to calculate the eigenvalue for the M equal to half state. So just put M equal to half here, and you will get the result easily. Okay, so that was a pretty straightforward question. The only thing was to express the Hamiltonian in a simple form that facilitates us to recognize the appropriate eigengates for the Hamiltonian. So here we recognized that the Hamiltonian eigengates can be taken as the simultaneous eigengates of S square and Sz. So I think there is no question on this one. So let us move on to the next one. Now the problems will start to be a little involved. So consider this. So this is not a question in assignments, but this kind of questions mm, you will encounter during competitive exams. Like this is the problem. So for spin to particle, let the Hamiltonian be this. So this is the Hamiltonian. Okay, so given this Hamiltonian, you have to find the energy levels. So the Hamiltonian is given as a linear combination of the spin angular momentum components. So Asx plus Bsy plus Csz. So ABC are real numbers, so that the Hamiltonian is what? Hermitian. So given this Hamiltonian, so find the energy levels. Now, can you tell me how to proceed? I mean, do you have any idea? Okay, so so before this question, so let us first look at this one. So this is a easy one. So the reason is that the concept that will be clear from the discussion of this question will be used in problem 3. So using the properties of the Pauli matrices, calculate or simplify this expression. So e to the power minus I pi by 2 sigma y multiplied by sigma z and e to the power I pi by 2 sigma y. So using the properties of the Pauli matrices, you can actually calculate this in a closed form. So of course you know the exponential of an operator is the expansion of that exponential in terms of the infinite power series. So like e to the power, so exponential of this operator is nothing but this exponential expansion. So nothing fancy. So here we will see that using the properties of the Pauli matrices, this will give us a very simple expression. So you see, when you expand this exponential, so e to the power x is 1 plus x squared by 2 plus x cubed by 3 factorial plus all these terms. So you see, we have to calculate the power, like the integer powers of this sigma dot n operator. So here n is a unit vector, theta is some real number, like it is the rotation angle, n is the unit vector, so nx square plus ny square plus nz square is equal to 1. So we have to calculate the integer powers of this operator. So let us begin with the square of this operator. So you know, so sigma dot n is this one. So this is nothing but vector dot product, where instead of scalar components, you have operator components in one of the vectors. So this ni are just numbers, the component of a vector, and sigma I are the Pauli matrices, which are operators. So, but the dot product is done in exactly the same way as you perform the scalar product of two vectors. So this is this. So this is sigma x nx plus sigma y ny plus sigma z nz. Okay. So this is summation of three terms multiplied by the same thing. This is again the summation of three terms. So you are actually then multiplying two series, each with three terms. So what do you expect when you multiply these two summations? So you expect to get 9 terms, right? Because 3 square like terms, like so when you take the square of x plus y plus z, so you get 9 terms actually, and then you find that out of those 9 terms, okay, so the cross terms are actually equal to each other, and those 6 cross terms reduces to 3 cross terms, and then you get 6 terms. So here also, so that is why, so when you multiply two series, you have to keep the dummy summation variables different for two series. Otherwise, you will not get those cross terms, and you will conclude that there are only square like terms. So that is why I have kept here the summation variable as I and here as j. Okay, now multiply the series. First, let us collect the terms for which I is not equal to j. So this is double summation, sum over I and sum over j, but I is not equal to j. So there are 6 terms in this summation, and then there are square like summation. So this is the summation for which I equal to j, and I is running from 1 to 3. So there are 3 terms in this summation. So 3 terms in this highlighted sum and 6 terms in this I not equal to j sum. So that gives you total 9 terms. So now let us proceed. So you know the property of the Pauli matrices. So sigma is sigma j when I is not equal to j is I epsilon ijk sigma k. Right? You know that. So epsilon ijk is the Levi-Civita symbol, and sigma I square is nothing but only the identity operator. So these two properties of the Pauli matrices are to be used. Okay. Now let us look at this term. And now we will use the property of the Levi-Civita symbol. Like you know, the Levi-Civita symbol is completely antisymmetric in all its indices. That means you exchange any two of its indices and you will get a minus sign, right? Like consider this. So this is E, so epsilon jik. So this is equal to minus epsilon ijk. So this is the minus sign. So this kind of antisymmetric properties. So now let us look at this summation. So you see, so okay, there should have been a summation over k also, but anyway. Okay. So let us first calculate the I not equal to j sum. So remember, so there is some I is going to 1 to 3, and j is also going from 1 to 3, but the condition is I and j cannot be equal. Okay, so now of course you can interchange the dummy variable also, because I and j are nothing but dummy variables of the summation. So you can rename I to be j and rename j to be I. So, but the final result of the summation will not change. So please compare these two terms and you will find that I have just written I to be j and j to be I. Fine. Now compare this and this term. So you know, so since nj and ni are ordinary numbers, so nj ni is equal to ni nj. So now multiplication of ordinary numbers commute. So nj ni is equal to ni nj. So that is what I have used here. Now finally we use the antisymmetry property of the Levi-Civita symbol. So epsilon jik is equal to minus epsilon ijk. So because we are interchanging j and I, okay, so remember, so earlier we just changed the label to relabel I as j and j as I, but now we are not relabeling, we are just manipulating the indices of the Levi-Civita symbol. So you can think these Levi-Civita symbols as like higher order tensors. So remember, for antisymmetric tensors you have mij is equal to minus mji. So this is the same thing. So epsilon jik is equal to minus epsilon ijk. So going from here to here, we are not relabeling the summation dummy indices, but we are using the antisymmetry property of the Levi-Civita symbols. Okay, fine. So starting from this, we reach this. But compare and you see that this is exactly minus of the thing that we have started from. So that means the highlighted thing has to be 0. Okay, so this is 0. That means this term is going to be 0. So the only non-zero term is this. And as we said, so ni was a unit vector. So that means summation ni square will be 1. So that means our final answer for the square of this operator is 0 plus identity is equal to identity. So that means sigma dot n whole square gives us identity. So using this property, the exponential expansion will reduce to a very simple result. Now you can easily see that, so since sigma dot n square is identity, that means sigma dot n to the power 2n is also identity, because this is the nth power of sigma dot n whole square, and identity to the power n is identity, and this is valid for any n greater than equal to 0, and sigma dot n to the power 2n plus 1 is simple sigma dot n, because up to 2n it was identity, then there is one more power and that gives you sigma dot n. So these two properties are to be used. Now expand the exponential. So this is the expansion for the exponential. Fine. So and now we can separate out the even powers and odd powers like this. So nothing. So this is simple. This is the simple exponential series. I have just written the even powers and odd powers separately. Okay, and for even powers, as we have just seen, so sigma dot n whole to the power 2n is identity. So from even powers you get this series, and from this odd power terms, using the fact that sigma dot n whole to the power 2n plus 1 is sigma dot n, you get this series. Okay, and okay, so the operator thing is brought out, and the summation thing, it is just a number. Similarly here also the summation thing is also just a number, so there is no operator that needs to be summed. So this is just two real series, two complex series, and we can recognize that the first one is the expansion for cos theta by 2, and this is the expansion for sin theta by 2. So that means collecting all these things, our final result is this. So exponential of I theta by 2 sigma dot n is equal to this simple operator. Okay, this is the result. So this has many uses, and using this result we can easily solve our problem. Like we have to find the exponential of I pi by 2 sigma y. So let us look how to find it from here. So e to the power plus minus I pi by 2 sigma y. So let us compare. So sigma dot n. So sigma dot n is sigma y here. Okay. Theta is pi, and or okay. So theta is plus minus pi. Theta is plus minus pi. So compare with this one. So theta is plus minus pi, and sigma dot n is only sigma y. So now if we put theta is equal to plus minus pi here, this gives us 0, and sin theta plus minus pi by 2 is plus minus 1. So this gives this, and sigma dot n is simply sigma y. So that means this is the result. E to the power plus minus I pi by 2 sigma y is equal to plus minus sigma y. Now we just have to multiply these three operators. Of course, this is nothing but sigma y, sigma z, sigma y. Now again use the properties of the Pauli matrices, like sigma y, sigma z is equal to I sigma x. Now finally multiply I sigma x sigma y, and you will get minus sigma z. So this is the final result. So note that we started with sigma z, okay, and we ended up with minus sigma z. So seems like there is a 180-degree rotation of sigma z. And you know the transformation, so this rotation is a transformation, right? So transformation on the operators are carried out with unitary operators of this thing. So e to the power minus I pi by 2 sigma y. So this is definitely a unitary operator, as you can check. So this has the form u dagger sigma z u. So we are unitary transforming sigma z to minus sigma z. So this unitary transformation amounts to 180-degree rotation. And we see that the rotation is about the y-axis by angle pi. So this is the rotation matrix, rotation operator in quantum mechanics. So this is the rotation operator in quantum mechanics. So if it acts on a state, so it rotates the state by angle, a spin half state actually. So for spin half you will use sigma by 2. For higher spin you will use the appropriate higher spin operators. So for spin half, for a spin half state, if you act this operator on that spin half state, you will rotate that spin half state by angle theta, and the rotation is done around the n vector direction. So n vector is the rotation axis, and around that axis you are performing a rotation by angle theta. So here also just see, and so this is the rotation operation on a state. And of course, so if you compare with the Schrodinger and Heisenberg pictures, so in Schrodinger picture, the time evolution of a state is given by e to the power minus iht by h cut, right? And in the Heisenberg picture, the time evolution of an operator is given by e to the power iht by h cut, that operator then multiplied by e to the power minus iht by h cut. So similar thing here also. So this is the operator that rotates the state, and the operator, so and to rotate an operator we have to consider this operation. So again, so u dagger operator and u. So if we look at this, so we find that this is the rotation around the y-axis and by angle pi. So so if you rotate the z component of a spin around the y-axis by angle pi, what do you get? So the direction of the earlier z components is just rotated by 180-degree, and then you get the minus sign that you are getting here. So this is the discussion on this mathematics. Now with this knowledge, we shall proceed to find the solution of problem 3. So in the meantime, if you have any question, please feel free to ask. Okay, so don't think so. So given this spin 2 particle with the Hamiltonian, that is a linear combination of spin angular momentum components. So we have to find the energy levels. So A, B and C are three real numbers, and this ensures that the Hamiltonian is Hermitian. Okay. So this is the Hamiltonian, a linear combination. And okay, so comparing with this problem, so here it is theta by 2 sigma dot n. So, and I said n is a unit vector. So can we consider that theta by 2 n vector is the, so theta by 2 is like the magnitude of the vector of which n is the unit vector. So we can certainly think it like that. So theta by 2 is the magnitude of the vector whose unit vector is n vector. So we shall rewrite this Hamiltonian in that form. Okay. So this is the linear combination of the three components of the spin angular momentum. So this can definitely be written as a vector dot product. Okay. So a square plus b square plus c square to the power half is the magnitude of that vector, and n is the unit vector of that vector. So this is the vector, and with this we are taking the dot product of the spin angular momentum vector operator. So this is our Hamiltonian. So now our job is to find the eigenvalues of this operator. So n vector dot s operator. Where n is the unit vector in a given direction. Now we have just seen that, so like compare with this earlier problem, like we have seen that, so this operation amounts to rotating the sigma z operator to minus sigma z operator, right? So you rotated the sigma z operator around y-axis by angle 180 degree, and that is how you got the minus sign. So that means you can reach this operator you can reach this operator by rotating your SZ operator. Like, is this point clear? Like, uh, in three-dimensional space, your ordinary three-dimensional Euclidean space, so we can reach a vector. We can reach a vector by performing a rotation, unless it is parallel. Okay. Okay, so you can reach this vector by rotating your SZ vector, like SZ component. And how to implement that rotation, as we have just discussed. So you have to act with the unitary operators like U, SZ, U dagger, and that will rotate your SZ to this new operator n vector dot s cap. So okay. So by performing a rotation, you can go from that SZ operator to this n vector dot s cap operator. And in quantum mechanics, the transformation of the operators are performed by unitary transformation. Now, as we have just said, that this n vector dot s cap operator and sz operator are actually, so they are actually connected by what? So they are actually connected by rotation. That means unitary operation, and we know that two unitary equivalent operators have same eigenvalues. Right? So consider this. So this is the statement. So an operator and its unitary transformed version has same eigenvalues. So if A is an operator and it has eigenvalue alpha, that means U dagger AU also have the same eigenvalues alpha. So how to see that? So it is very easy. So consider the eigenvalue eigenvector relation for an operator A. Okay, and now so we can think that this is I is the identity, and in place of identity insert a U dagger. Okay, so in place of the identity insert U dagger, and then again multiply both hand side by U dagger. So that means on the left hand side you have this. So remember, the leftmost U dagger is obtained after we multiply both hand sides by U dagger. So that means, now look at this eigenvalue eigenvector relation. So this says that U dagger AU operator has the same eigenvalue alpha, but now eigenkets are U dagger alpha. So eigenkets are unitary transformed, but the eigenvalues remain same. Now we shall use this concept. So as we have said, the SZ operator can be unitary transformed to the S dot n operator. So the eigenvectors will definitely be defined for these two, but the eigenvalues will remain unchanged. So that means we have to just write down what are the eigenvalues of our SZ operator. So what are the eigenvalues of the SZ operators? And those same eigenvalues will also be the eigenvalue of this n vector dot S vector operator. Okay, and we know for a spin to spin angular momentum operator, the SZ eigenvalues are this 0 plus minus h cut and plus minus 2h cut. So that means the n vector dot S vector eigenvalues will be these ones, same as those of the SZ. And now after we have found the n dot S eigenvalues, we can readily write down the energy levels by multiplying those with the norm of that vector. So the final answer is this. So nothing but we have just multiplied with the norm of this a comma b comma c vector. Okay. So this discussion shows that, so we have said that SZ and any S dot n operator will have same eigenvalues. So S dot n can be also Sx or Sy for some values of n. So that means Sx and Sy also have same eigenvalues as that of Sz. So all of these rotations in different along different axes have same eigenvalues, but their eigenvectors are different and are connected to each other by unitary transformations. So this concludes this question. So if you have any question, please ask. Okay, so if not, then finally we proceed to the problems involving the Stern-Gerlach physics. Like, yeah, okay. Question 4 is the discusses some preliminary concepts, and question 5 will actually be on a Stern-Gerlach setup. So consider this. A spin-up system is known to be in an eigenstate. Known to be in an eigenstate of. So there is an of missing. So a spin-up system is known to be in an eigenstate of this operator S dot n with eigenvalue plus minus h cut by 2. And n is the unit vector as in our previous problems, and we have given a precise representation of that unit vector, like this is the unit vector in theta naught phi naught direction, Now when Sx is measured, what is the probability that we get minus h cut by 2? Now look at the question. So this says that the spin-up system is known to be in an eigenstate of s dot n with eigenvalue h cut by 2. So we know that the Sz operator has eigenvalues plus minus h cut by 2, and the question also says that s dot n has also eigenvalue h cut by 2. Of course, if you remember the discussion of just the previous question, we will we anticipate that Sz and s dot n have same sets of eigenvalues. So that means the eigenvalues of s dot n will also be plus minus h cut by 2. And similarly for Sx also, the eigenvalues will again be plus minus h cut by 2. So we have to find the probability of getting h cut so minus h cut by 2 when we measure Sx, given that the system is in an eigenstate of s dot n with eigenvalue plus h cut by 2. Okay, so how to do it? So this is a simple spin-up system. So we can actually, try to solve the eigenvalue-eigenvector relation for this s dot n operator, because that will involve only the 2 cross 2 Pauli matrices. So those are very easy to manipulate. So what will we do? So we will try to find explicit forms of the eigenvectors of this operator s dot n. Okay, and then so after we find the eigenvectors of s dot n is a general direction, we can directly write the corresponding eigenvectors of this Sx operator also, and then we shall take the inner product of the Sn eigenkette with eigenvalue plus h cut by 2 with the Sx eigenbra with eigenvalue minus h cut by 2. Okay, so this is what we will do. So first we shall find the eigenvectors of this s dot n operator. Okay, so s dot n, so for spin-up system, S is nothing but h cut by 2 sigma matrices, right? Pauli matrices. So S is h cut by 2 sigma. Now s dot n is take the dot product between S and direction n. So this is the result of the dot product. Okay. And now we know the explicit expressions for these Pauli matrices in Sz eigenbasis. So we shall perform all the calculation in Sz eigenbasis. Okay. So we shall use the explicit forms of these Pauli matrices in Sz eigenbasis. So sigma x is given like this, sigma y is this, and sigma z is this. And they are valid in Sz eigenbasis. Okay. So, and nx, ny, nz. So these are the components of n. So this is the unit vector in represented in spherical polar coordinate, right? So just put the values of nx, ny and nz and add these three matrices, and you will get the matrix representation of the S dot n operator in Sz eigenbasis as this. So this is the matrix representation of S dot n in Sz eigenbasis. Now once we have this matrix representation, now all we need to do is to diagonalize it to find the eigenvalues and eigenvectors. So we already know the eigenvalues from our discussion of the previous questions. So they are plus minus h cut by 2, but we need to find the eigenvectors. So for that, let us go through the whole procedure of diagonalizing a 2 cross 2 matrix. So if lambda h cut by 2 is an eigenvalue, then this is the corresponding eigenvalue equation. Okay, so this is straightforward, and the solution of this is given by lambda equal to plus minus 1. Okay, so the eigenstate lambda plus with eigenvalue plus h cut by 2 is okay, so that eigenstate psi plus satisfy this relation because it has eigenvalue plus h cut by 2. So note this cos theta minus 1 in here. So there it was cos theta naught. Here it is cos theta naught minus 1. It is minus cos theta naught minus 1. So we have to find, we usually find the eigenvectors by inspection. So here also by inspection you will find that this linear combination is the eigenvector of S dot n with eigenvalue plus h cut by 2, where these plus and minus states are Sz eigenstates. Okay, so you know the Sz eigenstate in the Sz eigenbasis is represented by, so plus is represented by this column vector 1 0 and minus is represented by the column vector 0 1. So that is why we have written this sigma y as this linear combination. And similarly you can also find psi minus, you can also find this psi minus as this linear combination, and this corresponds to this minus h cut by 2 eigenvalue of this S dot n operator. Okay, so since these are the eigenvalues, okay, so that much is fine. Okay, so now the spin-up system is known to be in an eigenstate of S dot n with eigenvalue plus h cut by 2. So that means we now know in which state the spin-up system is in. Okay, so we have just found the corresponding eigenvector with eigenvalue plus h cut by 2. Now when Sx is measured, what is the probability of getting minus h cut by 2? Now we have to find, so for that we have to find the Sx eigenstate with eigenvalue minus h cut by 2 and take the dot product and do mod square with the 1 which we have just derived. So now we have to find the sigma x eigenvectors. So sigma x eigenvalues, we already know that they are also plus minus h cut by 2. So now we want to find the sigma x eigenstates. Now since we have just done the general calculation for, so we have just found the general eigenstates for uh, for an s dot n operator where n is any general direction, right? So you can choose theta naught and phi naught to be anything allowed, and you will get, so depending on theta naught and phi naught, you will get different states. Now how to, so for x direction, what do you have? So for this x direction is described by theta naught equal to pi by 2 and phi naught equal to 0, right? So theta naught equal to pi by 2 and phi naught equal to 0 gives you 1, 0, 0, and that is the x direction. Now in our general formula for the minus h cut by 2 eigenvalues, this is the general formula for minus h cut by 2 eigenvalues. In this formula, we just need to put theta naught equal to pi by 2 and phi naught equal to 0. Thus, the Sx eigenstate corresponding to the eigenvalue minus h cut by 2 is simply this linear combination. So 1 by root 2 plus ket minus minus ket. Now we have found the eigenvalue in which the system was originally in, and the eigenvalue, so and the eigenvector in which Now we have to find the probability of getting minus h cut by 2 in measuring Sx in the plus h cut by 2 eigenket of s dot n. So that means we have to find the probability of getting this state in the psi plus state, right? So what is the probability of getting this x minus state in the psi plus state? We find that by calculating the probability, and this is the formula for this probability. So inner product of these two states divided by the norms, and the norms are already unity in our case. So we have to now take the inner product between this, so between this and this. So take the inner product, do the mod square, and you will get this answer. So the answer is 1 by 2 multiplied by 1 minus sine theta naught cos phi naught. So this is the answer. I hope the steps that you need to perform is clear. So if that is the case, then let us move on to the next one. Or else, please ask a question. Okay, so let us move on to the Stern-Gerlach problem. So the problem statement is this. So a beam of spin-up atoms goes through a series of Stern-Gerlach type measurements as below. So it will go through 3 steps in this scenario. Like in step 1, so first measurement accepts Hz equal to h cut by 2 atoms and reject Hz equal to minus h cut by 2 atoms. After this first measurement, now the second measurement accepts Sn equal to h cut by 2 atoms and rejects Sn equal to minus h cut by 2 atoms. So Sn is our previous operator, like this is the rotation along n direction. So Sn is nothing but s dot n, so that operator. And then third measurement accepts Sz equal to minus h cut by 2 atoms and rejects Sz equal to h cut by 2 atoms. So this is the 3-step procedure. Now the question is, what is the intensity of this final Sz equal to minus h cut by 2 atoms if the Sz equal to h cut by 2 atoms surviving the first measurement is normalized to unity. So nothing to worry about upon looking at this word intensity. So this is just we shall just treat it as the probability as we are familiar with. So just replace intensity with our familiar word probability. So now we have to find the probability. So in this problem we shall use the results derived in problem 4. Like we have to use this result. So let's begin. So as is given in question, so first measurement accepts Hz equal to h cut by 2 atoms and reject Hz equal to minus h cut by 2 atoms. So that means after the first measurement, okay, and another thing is that we shall do all the analysis in the Hz eigenbasis. Okay, so after the first measurement, the state of the atoms are plus. So this is the eigenvector of Hz with eigenvalue plus h cut by 2, and that is what is said in question. Like first measurement accept Hz equal to h cut by 2 atoms. So after first measurement, the state of the atoms are this plus state. Now the second measurement accepts Sn equal to h cut by 2 atoms. So to find the intensity, so as we have said, intensity is nothing but probability. So to find the intensity after the second measurement, okay, so that means we have to find the survival probability of the atoms that is emitted after first measurement. So the atoms that are emitted after first measurement are all plus state atoms. So now we have to find the probability of the atoms to be in the uh, s dot n plus h cut by 2 state. So only those atoms which have s dot n eigenvalue h cut by 2 will be allowed to pass through after the second measurement. So we have to find that probability, and that will be the intensity also. So because you know, okay. So in the Einstein photoelectric effect interpretation, the intensity is the number of photons, right? So it had nothing to do with frequency, which was energy, but intensity was the number of photons. So similarly in this here also, the intensity will be the number of atoms that pass through, and the number of atom. So what is probability? So probability is out of a large number of atoms, what fraction of the atoms survive. So this is our usual familiar notion of probability. So here also we have to find the survival probability of the atoms after the second measurement, and that survival probability is actually the fraction of the atoms uh, that are allowed to pass through. So to find the intensity after the second measurement, we need to find the probability of finding this plus state in this n plus state. And from question 4, we saw that this n plus state is nothing but this linear combination. Okay, so this is this thing. So we have to find the probability of finding these plus states that emitted from the first measurement in the n plus states. So only those atoms that will be found in n plus state will be allowed to pass through after the second measurement. Now the probability of finding this plus state in this n plus state is nothing but this. This is the probability. So take the dot product of this n plus state with this plus state, and you will get this cos squared theta naught by 2. So I have just replaced the word probability with intensity as we discussed, and one is the original probability. So they normalized the intensity of the atoms that survived the first measurement to unity. So this is this unity. So the intensity of the beam emitting after the second measurement is this one, cos squared theta naught by 2. Okay. Now the beam is in this state. So the beam is in this n plus state when it enters the third measurement, right? So it is in this n plus state when it enters the third measurement. Now we have said that this third measurement accept this Sz minus h cut by 2 atoms and reject Sz equal to h cut by 2 atoms. So that means the final intensity will be proportional to the probability of finding these n plus states that enters the third measurement in the minus state. So in a sense, we have to find the probability of finding the n plus state in the minus state. And what is this intensity? Okay, so this is the quantum mechanical probability part. So probability of finding the n plus state in the minus state, just take the dot product and the result of the dot product. The non-zero result comes from this part. Take the mod square and the phase factors give you 1. So this, and multiply this with the probability, so with the intensity that enters the third measurement. So cos square theta naught by 2, and this part gives you sin square theta naught by 2, as you can see from here. Okay, so multiply them and your final result is this. So your final intensity will be 1 by 4 sin square theta naught. So, and the most puzzling thing is, so after the first measurement we rejected this Hz equal to minus h cut by 2 atoms, but after the third measurement, which accepts this Hz equal to minus h cut by 2 atoms, gives us a non-zero value for intensity. So classically we would have expected that this probability is going to be 0, but quantum mechanically we see that that is not the case. So the final intensity is a non-zero one, and the answer is this. And of course this is maximum when theta naught is pi by 2. That means when this n vector lies in the xy plane, that is when the angle theta naught is at 90 degree with the z axis, the final intensity will be maximum. So the final intensity is only 0 when theta naught is 0, and that is expected because then you are always in the Sz eigen states, and you have already rejected the Sz equal to minus h cut by 2 atoms. So the answer for this final intensity is almost always non-zero. So this concludes today's discussion. So if you have any question, please ask. Otherwise, we shall meet next week. Okay, so I think there is no more questions. So let me end today's session. Okay. So let us meet next week. I'm ending this call.